Okay, so let's talk about the $100 challenge problem that we had from the first lecture. So $100 challenge. Okay, remember what it was about. It was about finding matching subsets. Find subsets with matching sums. Okay, so let me remind you what the problem was. There are 100 numbers, x1, x2, x3, up to x100. And each of these were 27 digits. Numbers. So they're very big numbers. Okay. And the goal is to find two subsets, for example, x1 and x2, and then another subset could be x11 and x100, or, they could be different size subsets or whatever. So find me two subsets which have matching sums. Okay, interesting. And, I gave you this problem and I said, I'm going to put $100 on it. And then you might have thought, well, this guy's willing to give away $100. Maybe it's a wild goose chase. Maybe he's just, tricking us, evil professor that he is. And, he's going to focus us on this problem. And there's no way to find these subsets. In other words, maybe there are no two matching subsets. So we'll spend hours and hours and millennia and we wouldn't be able to solve the problem. So just like the 4-year-old who said, Dad, are you sure there's a cat in this picture? And I have to prove it to the 4-year-old. Okay. You should ask the same question of me. You say, well, are you sure that this problem is solvable? Is this problem solvable? Okay. And now I will prove to you, that this problem is solvable. And then you say, oh, wow, how are you going to do that? Are you going to show us the solution? No, that's the beauty of the proof. I'm going to prove to you that this problem is solvable without in any way giving you any hint whatsoever at what the solution is, what the subsets are, how to get the subsets. Okay? Just like I was challenged by the 4-year-old to prove that the cat exists in the picture without showing where the cat is, I'm going to show you that this problem is solvable. Okay? So, not only am I going to show you that the problem is solvable, I'm going to show you that the problem is solvable no matter what the choices you made for the numbers in the subset. For the numbers in the set. Okay. So, problem is solvable no matter what x1 up to x100 are, as long as, they are numbers that are not larger than 27-digit numbers. So they're all 27-digit numbers. Okay, so here's the proof. Okay, and it's a non-constructive proof. That's why you'll have no idea how to get them or what the subsets are from this proof, but it will be without any doubt a proof that's convincing you that the problem is solvable. So, let's think about a subset. Think about a subset. Okay. So a subset is, some subset of numbers like x1, x2, x3. And let's think about the sum of that subset. And its sum. Okay. So the maximum possible sum equals what? Well, the maximum possible sum is when the subset contains all the numbers. So the maximum possible sum is x1. They're all positive numbers. So it's x1 plus x2 plus x100. That's the maximum possible sum. Okay. And any 27-digit number is less than 10 to the 27. Just like any 2-digit number is less than 10 to the 2, which is 100. So any 27-digit number is less than 10 to the 27. So xi is less than 10 to the 27 because they're 27-digit numbers. So this maximum possible sum is less than 10 to the 27 times 100. Okay, times 100 because there are 100 numbers and they're each at most 10 to the 27. So this is equal to 10 to the 29. So the maximum possible sum is 10 to the 29. So let's list out all the possible sums. And if we ignore the empty subset, then all the possible sums, well, even 1 is not possible because they're all 27-digit numbers. But let me even start at 1. So all the possible sums are 1, 2, 3, 4, 5, and so on, all the way to 10 to the 29. The maximum possible sum. And if I listed this out, it would take me a long time. Okay. But what have I done? I've created a bin for every possible sum that a subset could sum to. Okay. There are no other possible sums. So there are 10 to the 29 bins here that correspond to subsets. So I'm going to think of these as bins. Okay. Now, those bins are going to play the role of my pigeonholes. Okay. I'm going to apply the pigeonhole principle, so I need to tell you what are my pigeons. Okay. So let's consider a subset. For example, x1, x2, x3. x1, x2, x3. That's a possible subset. It's going to have some sum. So there's going to be some sum. Okay, and the sum might be, whatever it is. Let's say, 19, billion, trillion, or something like that. Okay, so this sum, okay, can be computed. And then once I compute this sum, I can find the bin that corresponds to that sum, and I can place this subset in the corresponding bin. So place subset into bin for its sum. Okay, very nice. Okay, so, well, if I wanted to do a lot of work and accomplish nothing, I consider all possible subsets, okay, and I place each subset into its corresponding bin. When I do this for all possible subsets, so the subsets will occupy bins, and the subsets are going to be my pigeons. Okay, so the subsets, all the possible subsets are my pigeons. Okay. Well, how many possible subsets are there? And we think back to the previous lecture, the number of possible subsets of a 100 element set is 2 to the 100. So there are 2 to the power 100 possible subsets. But since I'm excluding the sum of 0, I'm excluding the empty subset. So there's 2 to the 100 minus 1 possible subsets. Okay, the 1 being the empty subset. And, this number, if we compute it, is approximately equal to 1.3 times 10 to the 30, which is strictly bigger than 10 to the 29. Okay, in fact, it's about 10 times bigger than 10 to the 29. What does that mean? It means that I have more subsets than bins into which I can place them. I have more pigeons than pigeonholes. What does that mean? The pigeonhole principle says that at least one of these bins will contain 2 or more subsets. So this means that at least one bin contains 2 or more subsets. So let's examine those 2 subsets that are in the same bin. Well, how did those 2 subsets get put in that bin? They got put in that bin because their subset sum was equal to the number of the bin. So that means that those 2 subsets have the same sum. They are matching subsets. End of proof. Indeed, look at that. So I have proved that there exist matching subsets without showing you in any way whatsoever how to get them. Miracle! I can show you that something exists. I can show you that a solution to this problem exists without telling you in any way how to get the solution, how to find the solution. And indeed, one of the mentors for this class has actually solved the problem and verified that that they can find 2 matching subsets. Fortunately for me, my $100 is still intact. Okay, because it's only open to students of the class, not mentors. Those guys have become professionals. So, but that's also fortunately for you. It means that the $100 is still up for grabs. So maybe you are re-energized now because you know that the solution exists. So go and find it. Okay. So what have we done? So the last lecture and this have been on counting. Counting is very important when it comes to sort of analyzing algorithms, especially brute force algorithms that do everything in every possible way. Okay. Now, so we discussed basic tools for counting, and then today we discussed slightly more advanced tools, repetitions in sequences, and also, we discussed this extension of the sum rule to when the sets can overlap. Okay, good. And we also see here now that counting, or a very simple counting principle, the pigeonhole principle, is not only useful for counting, but useful for proving deep things, the existence of deep things. And later, we will use the pigeonhole principle to prove the existence of problems that cannot be solved on certain kinds of computers. Okay. which then inspires us to seek more complex computers. And we'll keep playing that game until we get to a model of the actual digital computer that we currently have. Well, actually, we'll get to a model that's even more powerful than the digital computers that we currently have. Okay, so just a little appetizer to show you where counting will play some role when we come to the theory of computing. Okay, but having said all that, counting is very important. It can be hard to count certain things, but it's very interesting and a very beautiful subject. Okay, and so with that, read the chapters carefully, and I am checking out.